All right, let's talk about the biggest idea in physics for the last, half a century, string theory. The basic pitch is that everything, you, me, the stars, all of it, is made of these teeny, tiny, vibrating strings of energy. Sounds cool, right? But here's the thing. Some of the smartest people in the world have been working on this for 50 years. So how's it going? What's its report card actually look like?
Yeah, that's really the big question we're tackling today, isn't it? Is this thing the key to unlocking the entire universe, or is it just a beautiful dead end? I mean, we're talking about 50 years of physics basically going down one road. The stakes, they really couldn't be higher. And make no mistake, it has been a massive bet. For decades, this was the game in town for theoretical physics. If you were looking for that theory of everything, this was where all the action was. It completely captured everyone's imagination. So you gotta wonder, what's the big deal? Why would so many brilliant people bet their entire careers on something that, well, we can't definitively prove? What is it about this theory that's just so magnetic?
Well, to really get it, you have to look at the wins, and believe me, there have been some absolute stunners. These are the elegant, almost magical moments that keep the whole dream of string theory alive.
We're going to look at 3 of its greatest hits. First up, how it just gives you gravity for free. Then we'll talk about what it says about black holes. And finally, we'll get into this wild idea that the universe is basically a hologram. Yeah, seriously. Okay, let's start with its biggest win by far, gravity. See, for like 100 years, physics has had this massive headache. You've got Einstein's theory of gravity, general relativity, which describes the big stuff, and then you have the super weird rules of quantum mechanics for the tiny stuff. The problem? They just don't get along. So to get these two theories to play nice, you need a messenger particle for gravity, something called the graviton. For years, physicists tried to just cram it into their theories. It was awkward, it didn't fit, but with string theory, they didn't have to do a thing. The graviton just pops out of the math. It appears naturally as just another vibration of a string. I mean, can you imagine? For physicists, this was an absolutely jaw-dropping moment. Next up, black holes. You know, these cosmic monsters. One of the biggest puzzles about them is what happens to all the stuff, the information that falls in. Well, string theory gives us a way to build a model of a black hole from the ground up and actually count its insides, its quantum states. And the craziest part? The answers it spits out perfectly match predictions that Stephen Hawking himself made decades earlier. It's an incredible connection. And this third one, this one is going to bend your brain a little. It's called the hologram principle. What string theory found was this totally shocking mathematical link, a secret backdoor between 2 completely different kinds of theories. One is a complex theory with gravity, like our universe. The other is a much simpler particle theory without gravity, living in one less dimension. And the math says they're the same thing. They're equivalent. It's like our whole universe could be a 3D projection of a flatter, simpler reality. Wild, right? So, okay, it predicts gravity out of thin air, it helps us understand black holes, and it hints that we're living in a hologram. It sounds pretty amazing. But, and this is a big but, there are some really deep, really unsettling problems. The last couple of decades have not been kind to string theory. The cracks are starting to show. And just like with the wins, we can group the problems into 3 big categories. First, it predicts way too many particles that we've never seen. Second, it completely missed one of the biggest astronomical discoveries ever. And third, it doesn't predict our universe. It predicts an almost infinite number of them. All right, let's tackle that first problem. Too many particles. For the math in string theory to hang together, it needs something called supersymmetry. Now, what that means, basically, is that every particle we know and love, the electron, the photon, all of them, should have a heavier superpartner, a shadow particle. This would literally double the number of fundamental particles, adding at least 25 new ones to the list. Which leads to the obvious question, where are they? Seriously, we've built things like the Large Hadron Collider, these gigantic machines, and we have been looking for decades. And you know what we found? Nothing. Zilch. Not a single one of these superpartners. That is a huge problem for the theory. If they exist, they're hiding way better than anyone expected. And that kind of kills the whole elegance argument. Okay, problem number 2, dark energy. Back in the late 90s, astronomers made this shocking discovery that the universe isn't just expanding, it's speeding up. Something is pushing everything apart, and we call it dark energy. Now think about it. If you're selling your theory as the ultimate theory of gravity in the cosmos, you probably should have seen that coming. But string theory, It had no idea. It was completely blindsided.
And this last one, this might be the most troubling of all. It's called the landscape problem. See, you'd hope that your theory of everything would have one solution, right? The one that describes our universe? Well, string theory doesn't have one solution. It has maybe 10 to the power of 500. That's a 1 with 500 zeros after it. Each one describes a different possible universe with its own unique laws. So instead of predicting our universe, it predicts a near infinite landscape of possibilities with no guide to finding our own.
So you've got these incredible wins on one side and these devastating failures on the other. The theory is basically on trial. You've got supporters who say the math is just too beautiful to be wrong, while a growing number of physicists feel pretty disillusioned. So where does the search for a theory of everything go from here?
Well, these challenges have forced a really interesting change in tactics. The old way was bottom-up. Build the whole complicated string theory and then cross your fingers and hope it matched reality. The new bootstrap approach is top-down. It starts by just listing the absolute, non-negotiable rules that any valid theory of quantum gravity must obey.
And the hope here is pretty clever. By defining all the rules of the game first, physicists hope they can prove that string theory isn't just an option, but the only possible theory that fits all the constraints. It's an attempt to corner the answer, to show that any valid theory of quantum gravity has to look just like string theory.
And that leaves us here, right at the frontier of physics. Is this half-century bet about to pay off? Or will string theory be remembered as a beautiful, mathematically rich detour that led science down the wrong path? Only time will tell, but you can be sure the answer is going to define the future of physics.